Now, a system of linear equations can be written as an augmented matrix. So if I have the equation x plus 3y plus 2z equals 1, 2x plus y minus z equals 2, and x plus y plus z is 2, I can write this as what we're going to call an augmented matrix by taking the coefficients of the first equation and putting them in the first row, and the coefficients of the second equation and putting it in the second row, and the coefficients of the third equation and putting them in the third row. Now, you see the equal sign? We tend to put a straight line that reminds us that these are what is equal. These are our constants. Now, to do row matrix transformations, we can solve an augmented matrix and by exchanging any two rows, by multiplying or dividing the elements of any row by a non-zero real number, and replacing any row of a matrix by the sum of the elements of that row and a multiple of the elements of another row. Now, the Gauss-Jordan method tells us that it's just a process for solving these. The first step is to always get a 1 in the first element of the first column, and use the first row now to transform the remaining entries so that the first column is 0 everywhere except that first row. The next step is we want to get a 1 in the second entry in the second column, and use the second row then to transform the remaining entries of that column to 0 and keep going until you have a matrix that has ones along the diagonal. So this is called diagonal form or reduced row echelon form. And you see, this is really nice because when we have this, we can easily see that A is equal to 1 and B is equal to 1. A is equal to 1 in these cases, B is equal to 1, and C is equal to 1. Now, when a matrix methods are used to solve a system of equations, we're trying to get it written in diagonal form. There are three cases. If the number of rows with non-zero elements to the left of the vertical line is equal to the number of variables, then the system has a single solution. If one of the rows has all zeros, then the system has no solution. If there are fewer rows in the matrix containing non-zero elements than the number of variables, then the system has either no solution or infinitely many solutions. So let's solve the system 2x plus 3y equals 7 and 3x minus 4y equals negative 32. The first thing we're going to do is write the augmented matrix. So we're going to take the coefficients 2, 3, 7 and make the first row. And the second equation, 3, negative 4, negative 32 is our second row. Now we want a 1 in the first position, so I'm going to multiply the first row by 1/2. And so the first row becomes 1, 3/2, 7/2. So to do the Gauss-Jordan method, you introduce 0 in the second row, first column, by multiplying each element in the first row by negative 3, and then adding the result to the corresponding elements of the second row. So when I do this, so that's negative 3r1 plus r2, that gives me negative 17/2 equals minus 85 over 2. Now I want 1 in the second row, second column, and I can do that by multiplying the entire row by minus 2/17. Now I want to get a 0 in the first row, second column. And I'm going to do that by multiplying each element of the second row by negative 3/2 and adding it to the first row. And when I do that, I get a negative 4. So what this tells me is my x value is equal to -4 and my y value is equal to 5. Because this is literally 1x is -4 and 1y is equal to 5. So suppose I want to solve the system x plus y minus 4 equals 10 and 2x minus 3y plus z equals 7 and 3x minus y minus z is 12. Write down the augmented matrix. Remember, we're trying to get it in reduced row echelon form. So there's already a 1 in the first row, first column. So we're going to multiply um, the first row by -2 and add that to R2 and replace it into R2. We want to multiply through by -1/5 R2 in order to get this coefficient right here to be 1. Now I want to multiply each entry in row 3 by -3 and add the result to the third row to get a 0 in the first column. So -3R1 plus R3, I put it in the third row. Now I want to multiply each entry in the second row by 4 and add it to the third row to get a 0 in the second column, third row. And now I need to get this to be a 1, so I need to multiply the third row by 5/9. Now you see I have it in, I have a 1 across all of the diagonals. So now I'm going to multiply each row each entry in the third row by 9/5 and add it to the second row. So it'll be 9/5 R3 plus R2. We'll eliminate that variable. Next, I'm going to subtract row 2 from row 1 and put it in row 1. Next, I'm going to multiply R1. I'm going to multiply R3 by 4 and add it to R1. And that gives me my solution in row echelon form. So this tells me that x is 3, y is -1, and z is -2. Now suppose I want to use the Gauss-Jordan method to solve the system 2x minus 3y is 7 and 6x plus 9y is 0. You put it in augmented form. If I were to add 3 times R1 plus R2, I see that I get 0x plus 0y equals 21, which has no solution. Now suppose I try the Gauss-Jordan method with 2x plus y plus z equals 5 and 3x plus 2y minus z equals -8. I immediately see I don't have enough equations, so I'm going to have an infinite solution. But let's write our augmented system anyway. Let's do -3R1 and add it to 2R2 to get my first one there. And now let me add R1 minus R2 and then do 1/2 R1. Now we really can't go any further. So the equations that correspond are x plus 3z equals 18 and y minus 5z equals 31. You can solve these for x and y and get x is minus 3z plus 18 and y is 5z minus 31. And so the solution set is minus 3z plus 18, 5z minus 31, z.